So hopefully this video will explain a little bit about voltage regulators and certain circuitry and power supplies that regulate circuits. Now if we look down here, imagine if you will a transistor that's turned on, and its sort of equivalent can be seen as the two diodes. And the important thing here is to look at the voltage between the base and the collector. Now we don't know sort of what circuitry is going on here, but if we apply 1 volt at the base, due to the diode drop of, I'm assuming here, 0.7 in this generic sort of NPN transistor, we get 0.3 volts at the base, or the collector rather, and you know, that's set in stone, that's standard. That node's always going to be 0.3 volts of whatever the base is. Now, if we go down here, and using some Ohm's law off there, we can control the voltage at that collector. Now, like say if we put 101 volt on the base, it's still going to be 100.3 volts. If we use 10 volts here, through the calculated values of R1 and R2 over here of 390 and 570 ohms, we can create a voltage point that's 5.7 volts. Now, why did I choose 5.7? Well, if you got to remember, let's say we want 5 volts on this point here, a smooth 5 volts, 5 volts even, for whatever reason our circuitry needs 5 volts regulated. You have to account for the diode junction voltage drop there. So 5.7. Anyway, you design that, and I'm assuming a base current of 1 milliamp here, and I'm running 10 milliamps through the other resistor and 11 through the divider, so that way it's pretty stiff and it's not going to drift very much. So if we apply that down here in our circuit, 10 volts, the resistors, we get 5 volts for our resistive load. Now, sort of, why do we do this? You may have seen this before. Why don't I just do that, and I have a 5.7 volts? Well, that's fine and dandy, but these values are only start creeping up in here because I'm using very low currents here, and the fact that this resistor, if this was our load, for example, not the base of the transistor, but if this was our load, the resistance could vary depending on what the load's doing. If it's a light bulb, as it heats up, the current change, or the resistance changes, which changes the current. And these resistors would have to be a fairly substantial value. However, down here in this transistor, we could just put a big beefy power transistor and call it done. And so, meanwhile, only milliamps are flowing down here to give us a pretty stable voltage, and you probably could even put a little capacitor over here. I've also heard this referred to as a capacitor multiplier. But anyway, that point will give us a stable 5 volts for our resistive load. And you can even have a little bit of an adjustable supply by using a variable resistor for your load. Because say like I said earlier, that our load's changing by quite a bit for some reason. If the resistance goes up and you need to lower the voltage to keep the voltage constant, well, you can just go in there and tweak the resistor. Let's say the current's gone down again, and so the voltage is starting to creep back up. Well, you can go in there and turn back up the resistor. Now that's kind of annoying. You have to go in there and tweak it. What if we have a fast changing current drawing thing, like some sort of maybe microcontroller where there's a lot of noise and stuff has to act faster, and you can get your screwdriver down in there and turn it. Well, let's look at another device real fast, the Zener Diode. What's different? Well, one of the things that are different between this diode and your normal silicon diode is that it has a different voltage drop. And here, you can see I have it as A volts. They make various different Zener diodes with different voltage drops. 4.7 is a common one, 9, different things like that. And essentially, what that means is this thing won't start conducting until that voltage point is received, and when there's that voltage drop across it, so to speak, it won't start conducting, which is a great way of regulating of certain voltage. Now, obviously, these things, I don't know if you can look up pictures of them online, they're just a little glass tube, and if you're trying to power something in the amps range, you're going to blow it up and really make a show of everything. Anyway, we can use them with a transistor, same as before. Use that, and a bit of a variable resistor down here as a fine voltage adjust, which I'll explain in a minute. And this gives us a super stable base voltage for a what your load may change, and so this gives you a very steady 5 volts. Anyway, some of these Zener diodes, they're not perfect, as things are. These power transistors may not be perfect, and so the idea of this fine voltage adjust is you can have a little voltmeter across your load, and tweak the voltage, that little variable resistor. And what you're doing is, say you have say this is a 4.7 voltage drop Zener diode, right? If this was nil, if this was connected straight to ground, that would mean this point's always going to be at 4.7, which means with the 0.7 drop, this is going to be at 4. So that's not good. However, if we have enough resistance here to turn this resistor up, so there's a 1 volt drop across here, the total sum between this node and ground would be 5.7 volts, which is about perfect for the 0.7 drop, giving us our 5 volts that are regulated. And when you have like I've done over there, changing load with a variable resistor, it kind of helps smooth things out quite a bit. And it's going to be a lot more stable than the other resistor supply. If we look over here at this schematic, a lot of these things, like these resistors, if they start heating up due to, passing high current, underrated, whatever, or just temperature conditions like out in the field, if it's the dead of winter or if it's the middle of summer, those resistor values, especially the cheap kind, will start drifting in and out of tolerance. And so it's with the Zener diode, they don't drift in and out like that too substantially, or nothing. For practical purposes, if something's strong, a couple of amps, it's probably not worrying about that precise a voltage anyway. But that's sort of an introduction, without too much math, about how exactly we can get pretty good voltage regulation, just using this whole theory of the voltage drop from the base to the collector. It's always going to be 0.7, and we just let all this circuitry, if we just look down here, do whatever's connected to the base, let that select the voltage, and if it can give us a couple of milliamps of drive, we can power a transistor here that's can control a couple of amps, if not more. You can add another one and do what there's called a Darlington Pair, and instead of a gain of 100, you have a gain of 1,000 with 2 appropriately matched transistors, which are 2 transistors with the same beta value. But that's a topic for another video. Anyway, I hope you enjoyed this one, and I know it's fairly short, but maybe it'll bring some ideas to mind, and maybe open some new windows. Thanks for watching.